Chapter 3: Atoms and Molecules. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India. Around 500 BC, an Indian philosopher, Maharshi Kanath, postulated that if we go on dividing matter, Padarth, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pakudha Katamma, elaborated this doctrine and said that these particles normally exist in a combined form, which gives us various forms of matter. Around the same era, ancient Greek philosophers Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these indivisible particles atoms, meaning indivisible. All this was based on philosophical consideration and not much experimental work to validate these ideas could be done till the 18th century. By the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Antony L. Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combination. 3.1 Laws of chemical combination. The following two laws of chemical combination were established after much experiments, experimentations by Lavoisier and Joseph L. Proust. 3.1.1 Law of conservation of mass. In there, a change in mass when a chemical reaction takes place. Activity 3.1 Do this. Take one of the following sets X and Y of chemicals X, Y. 1 copper sulfate 1.25 gram, sodium carbonate 1.43 gram, 2 barium chloride 1.22 gram, sodium sulfate 1.53 gram, 3 lead nitrate 2.07 gram, sodium chloride 1.17 gram. Prepare separately a 5% solution of any one pair of substances listed under X and Y each in 10 milliliter in water. Take a little amount of solution of Y in a conical flask and some solution of X in an ignition tube. Hang the ignition tube in the flask carefully so that the solution do not get mixed. Put a cork on the flask. See figure. Cork, thread, conical flask, a small ignition tube, solution of X, solution of Y. Figure, ignition tube containing solution of X dipped in a conical flask containing solution of Y. Weigh the flask with its contents carefully. Now tilt and swirl the flask so that the solution X and Y get mixed. Weigh again what happens in the reaction flask. Do you think that a chemical reaction has taken place? Why should we put a cork on the mouth of the flask? Does the masses does the mass of the flask and its contents change? Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. 3.1.2 Law of constant proportion. Lavoisier, along with other scientists, noted that many compounds were composed of two or more elements and each such compound had the same elements in the same proportions irrespective of where the compound came from or who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8. Whatever the source of water, thus if 9 gram of water is decomposed, 1 gram of hydrogen and 8 gram of oxygen are always obtained. Similarly, in ammonia, nitrogen and hydrogen are always present in the ratio 14:3 by mass, whatever the method or the source from which it is obtained. This led to the law of constant proportions, which is also known as the law of definite proportions. This law was stated by Proust as in a chemical substance, the elements are always present in definite proportions by mass. The next problem faced by scientists was to give appropriate explanation of these laws. British chemist John Dalton provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportion. John Dalton. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later, he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics, and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. According to Dalton's atomic theory, all matter, whether an element, a compound, or a mixture, is composed of small particles called atoms. The postulates of this theory may be stated as follows. 1. All matter is made of very tiny particles called atoms, which participate in chemical reactions. 2. Atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. 3. Atoms of a given element are identical in mass and chemical properties. 4. Atoms of different elements have different masses and chemical properties. 5. Atoms combine in the ratio of small whole numbers to form compounds. 6. The relative number and kinds of atoms are constant in a given compound. You will study in the next chapter that all atoms are made up of still smaller particles. Questions 1. Do this and comment this. 2, 3, 4. Comment this. 3.2. What is an atom? Have you ever observed a mason building walls? From these walls a room and then a collection of rooms to form a building. What is the building block of the huge building? What about the building block of an ant hill? It is a small grain of sand. Similarly, the building blocks of all matters are atoms. How big are atoms? Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms when stacked would make a layer barely as thick as this sheet of paper. Atomic radius is measured in nanometers. 1 by 10 to the power 9 meter equal to 1 nanometer. 1 meter equal to 10 to the power 9 nanometer. Relative sizes. Radi and matter. Example. 10 to the power minus 10 atom of hydrogen, 10 to the power minus 9 molecule of water, 10 to the power minus 8 molecule of hemoglobin, 10 to the power minus 4 grain of sand, 10 to the power minus 3 ant, 10 to the power minus 1 apple. We might think that if atoms are so insignificant in size, why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surface of elements showing atoms. Figure an image of the surface of silicon. 3.2.1 What are the modern day symbols of atoms of different elements? Dalton was the first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element, that is, one atom of that element. Berzelius suggested that the symbols of elements be made from one or two letters of the name of the element. Hydrogen, carbon, oxygen, phosphorus, sulfur, iron, copper, lead, silver, gold, platinum, mercury. Figure. Symbols for some elements as proposed by Dalton. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from specific color. For example, gold was taken from the English word meaning yellow. Nowadays, IUPAC, International Union of Pure and Applied Chemistry, is an international scientific organization which approves names of elements, symbols, and units. Many of the symbols are the first one or two letters of the element's name in English. The first letter of a symbol is always written as a capital letter, uppercase, and the second letter as a small letter, lowercase. For example, 1 hydrogen H, 2 aluminium Al and not Al, 3 cobalt CO and not CO. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Examples are 1 chlorine Cl, 2 zinc Zn, etc. Other symbols have been taken from the names of elements in Latin, German or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is Na from natrium, potassium is K from kalium. Therefore, each element has a name and a unique chemical symbol. Table. Symbols for some elements. Element symbol. Element symbol. Element symbol. Aluminium Al, argon Air, barium Ba, boron B, bromine Br, calcium Ca, carbon C, chlorine Cl, cobalt Co, copper Cu, fluorine F, gold Au, hydrogen H, iodine I, iron Fe, lead Pb, magnesium Mg, neon Ne, nitrogen N, oxygen O, potassium K, silicon Si, silver Ag, sodium Na, sulfur S, uranium U, zinc Zn. The above table is given for you to refer to whenever you study about elements. Do not bother to memorize all in one go. With the passage of time and repeated uses, you will automatically be able to reproduce the symbols. 3.2.2 Atomic Mass. The most remarkable concept that Dalton's atomic theory proposed was that of the atomic mass. According to him, each element had a characteristic atomic mass. The theory could explain the law of constant proportion so well that scientists were prompted to measure the atomic mass of an atom. Since determining the mass of an individual atom was a relatively difficult task, relative atomic masses were determined using the laws of chemical combinations and the compounds formed. Let us take the example of a compound carbon monoxide CO formed by carbon and oxygen. It was observed experimentally that 3 gram of carbon combines with 4 gram of oxygen to form CO. In other words, carbon combines with 4 by 3 times of its masses of oxygen. Suppose we define the atomic mass unit earlier abbreviated as AMU, but according to the latest IUPAC recommendation, it is now written as U, unified mass, as equal to the mass of one carbon atom. Then we would assign carbon an atomic mass of 1.0 U and oxygen an atomic mass of 1.33 U. However, it is more convenient to have these numbers as whole numbers or as near to a whole numbers as possible. While searching for various atomic masses units, scientists initially took 1 of 16 of the mass of an atom of naturally occurring oxygen as the unit. This was considered relevant due to two reasons. Oxygen reacted with a large number of elements and formed compounds. This atomic mass unit gave masses of most of the elements as whole numbers. However, in 1961, for a universally accepted atomic mass unit, carbon-12 isotope was chosen as the standard reference for measuring atomic masses. One atomic mass unit is a mass unit equal to exactly 1/12 1 by 12 the mass of one atom of carbon-12. The relative atomic masses of all elements have been found with respect to an atom of carbon-12. Imagine a fruit seller selling fruits without any standard weight with him. He takes a watermelon and says this has a mass equal to 12 units. 12 watermelon units or 12 fruits mass units. He makes 12 equal pieces of the watermelon and finds the mass of each fruit he is selling. Relative to the mass of one piece of the watermelon, now he sells his fruit by relative fruit mass unit FMU. As in figure A, B, C, D. A watermelon figure B. 12 pieces, say 1 by 12 of watermelon. D. How the fruit seller can weigh the fruits using pieces of watermelon. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom as compared to 1 by 12th the mass of one carbon 12 atom. Table atomic masses of a few elements. Element atomic mass U, hydrogen 1, carbon 12, nitrogen 14, oxygen 16, sodium 23, magnesium 24, sulfur 33, chlorine 35.5, calcium 40. 3.2.3 How do atoms exist? Atoms of most elements are not able to exist independently. Atoms form molecules and ions. These molecules or ions aggregate in large numbers to form the matter that we can see, feel or touch. Questions 1, 2. Comments. 3.3 What is a molecule? A molecule is in general a group of two or more atoms that are chemically bonded together, that is, tightly held together by attractive forces. A molecule can be defined as the smallest particle of an element or a compound that is capable of an independent existence and shows all the properties of that substance. Atoms of the same element or of different elements can join together to form molecules. 3.3.1 Molecules of elements. The molecules of an element are constituted by the same type of atom. Molecules of many elements such as argon, air, helium, He, etc. are made up of only one atom of that element. But this is not the case with most of the non-metals. For example, a molecule of oxygen consists of two atoms of oxygen and hence it is known as a diatomic molecule, O2. If three atoms of oxygen unite into a molecule instead of the usual two, we get ozone, O3. The number of atoms constituting a molecule is known as its atomicity. Metals and some other elements such as carbon do not have a simple structure but consist of a very large and indefinite number of atoms bonded together. Let us look at the atomicity of some non-metal. Table: atomicity of some element. Type of element. Name: atomicity. Non-metal: argon, monoatomic helium, monoatomic oxygen, diatomic hydrogen, diatomic nitrogen, diatomic chlorine, diatomic phosphorus, tetraatomic sulfur, polyatomic. 3.3.2 Molecules of compounds. Atoms of different elements join together in definite proportion to form molecules of compounds. Few examples are given in table. Table: molecules of some compounds. Compound combining elements. Ratio by mass. Water H2O, hydrogen oxygen 1:8, ammonia NH3, nitrogen hydrogen 14:3, carbon dioxide CO2, carbon oxygen 3:8. Activity 3.2. Do this. Refer to table 3.4 for ratio by mass of atoms present in molecules and table 3.2 for atomic masses of elements. Find the ratio by number of the atoms of elements in the molecules of compounds given in table. The ratio by number of atoms for a water molecule can be found as follows. Element ratio by mass, atomic mass U, mass ratio or atomic mass, simplest ratio. H 1 1 1 by 1 equal to 1 2. O 8 16 8 by 16 equal to 1 by 2 1. Thus, the ratio by number of atoms for water is H:O equal to 2:1. 3.3.3 What is an ion? Compounds composed of metals and nonmetals contain charged spaces. The charged spaces are known as ions. Ions may consist of a single charged atom or a group of atoms that have a net charge on them. An ion can be negatively or positively charged. A negatively charged ion is called an anion and the positively charged ion a cation. Take for example sodium chloride NaCl. Its constituent particles are positively charged sodium ions Na+ and negatively charged chloride ion Cl-. A group of atoms carrying a charge is known as a polyatomic ion. Table. We shall learn more about the formation of ions in chapter 4. Table: some ionic compounds. Ionic compounds constituting elements. Ratio by mass. Calcium oxide, calcium and oxygen 5:2. Magnesium, magnesium, magnesium sulfide, magnesium and sulfur 3:4. Sodium chloride, sodium and chlorine 23:35.5. 3.4 Writing chemical formula. The chemical formula of a compound is a symbolic representation of its composition. The chemical formula of different compounds can be written easily. For this exercise, we need to learn and symbols and combining capacity of the elements. The combining power or capacity of an element is known as its valency. Valency can be used to find out how the atoms of an element will combine with the atoms of another element to form a chemical compound. The valency of the atom of an element can be thought of as hands or arms of that atom. Human beings have 2 arms and an octopus has 8. If one octopus has to catch hold of a few people in such a manner that all the 8 arms of the octopus and both arms of all the humans are locked, how many humans do you think the octopus can hold? Represent the octopus with O and humans with H. Can you write a formula for this combination? Do you get OH4 as the formula? The subscript 4 indicates the number of humans held by the octopus. The valencies of some common ions are given in table. We will learn more about valency in the next chapter. Table: names and symbols of some ion. Valency: symbol of ion, symbol, non-metallic element, symbol, polyatomic ions, symbol. 1. Sodium Na+, potassium K+, silver Ag+, copper I, Cu+, hydrogen H+, hydride H-, chloride Cl-, bromide Br-, iodide I-, ammonium NH4+, hydroxide OH-, nitrate NO3-, hydrogen carbonate HCO3-. 2. Magnesium Mg2+, calcium Ca2+, zinc Zn2+, iron 2 Fe2+, copper 2 Cu2+, oxide O2-, sulfide S2-, carbonate CO32-, sulfite SO32-, sulfate SO42-. 3. Aluminium Al3+, iron 3 Fe3+, nitrite N3-, phosphate PO43-. Some elements show more than one valency. A Roman numeral shows their valency in a bracket. The rules that you have to follow while writing a chemical formula are as follows. The valencies or charges on the ion must balance. When a compound consists of a metal and a non-metal, the name or symbol of the metal is written first. For example, calcium oxide CaO, sodium chloride NaCl, iron sulfide FeS, copper oxide CuO, etc. Where oxygen, chlorine, sulfur are non-metals and are written on the right, whereas calcium, sodium, iron and coppers are metal and are written on the left. In compounds formed with polyatomic ions, the number of ions present in the compound is indicated by enclosing the formula of ion in a bracket and writing the number of ions outside the bracket. For example, MgOH2. In case the number of polyatomic ion is 1, the bracket is not required. For example, NaOH. 3.4.1 Formula of simple compounds. The simplest compounds, which are made up of 2 different elements, are called binary compounds. Valencies of some ions are given in table 3.6. You can use this to write formula for compound. While writing the chemical formula for compounds, we write the constituent elements and their valencies as shown below. Then we must cross over the valencies of the combining atoms. Examples: 1. Formula of hydrogen chloride. Symbol HCl. Valency 1, 1. Formula of the compound would be HCl. 2. Formula of hydrogen sulfide. Symbol HS. Valency 1, 2. Formula H2S. 3. Formula of carbon tetrachloride, symbol CCl, valency 4 1. Formula CCl4. For magnesium chloride, we write the symbol of cation Mg2 plus, first followed by the symbol of anion Cl minus. Then their charges are crisscrossed to get the formula. 4. Formula of magnesium chloride, symbol Mg, Cl, charge 2 plus 1 minus, formula MgCl2. Thus, in magnesium chloride, there are two chlorides ions Cl minus. For each magnesium ions Mg2 plus, the positive and negative charges must balance each other and the overall structure must be neutral. Note that in the formula, the changes on the ions are not indicated. Some more examples. A. Formula for aluminium oxide, symbol AlO, charge 3 plus 2 minus, formula Al2O3. B. Formula for calcium oxide, symbol CaO, charge 2 plus 2 minus. Here the valencies of the two elements are the same. You may arrive at the formula Ca2O2, but we simplify the formula as CaO. C. Formula of sodium nitrate, symbol or formula NaNO3, charge 1 plus 1 minus, formula NaNO3. D. Formula of calcium hydroxide, symbol or formula CaOH, charge 2 plus 1 minus, formula CaOH whole 2. Note that the formula of calcium hydroxide is CaOH whole 2 and not CaOH2. We use brackets when we have two or more of the same ions in the formula. Here the bracket around OH with the subscript 2 indicates that there are two hydroxyl OH groups joined to one calcium atoms. In other words, there are two atoms each of oxygen and hydrogen in calcium hydroxide. E. Formula of sodium carbonate, symbol or formula NaCO3, charge 1 plus 2 minus, formula Na2CO3. In the above example, brackets are not needed if there is only one ion present. A formula of ammonium sulfate, formula NH4SO4, charge 1 plus 2 minus, formula NH4 whole 2 SO4. Questions 1, 2. Comment this. 3, 4. Comment this also. 3.5 Molecular mass and mole concept. 3.5.1 Molecular mass. In section, we discussed the concept of atomic mass. This concept can be extended to calculate molecular masses. The molecular mass of a substance is the sum of the atomic masses of all the atoms in a molecules of the substance. It is therefore the relative mass of a molecule expressed in atomic mass units U. Example 3.1. Calculate the relative molecular mass of water H2O. B. Calculate the molecular mass of HNO3. Solution. A. Atomic mass of hydrogen equal to 1U, oxygen 16U. So the molecular mass of water, which contains 2 atoms of hydrogen and 1 atom of oxygen, is equal to 2 into 1 plus 1 into 16 equal to 18U. B. The molecular mass of HNO3 equal to the atomic mass of H plus the atomic mass of N plus 3 into the atomic mass of O equal to 1 plus 14 plus 48 equal to 63U. Three 3.5.2 Formula unit mass. The formula unit mass of a substance is the sum of the atomic masses of all atoms in a formula unit of a compound Formula unit mass is calculated in the same manner as we calculate the molecular mass. The only difference is that we use the word formula unit for those substances whose constituent particles are ions. For example, sodium chloride, as discussed above, has a formula unit NaCl. Its formula unit mass can be calculated as 1 into 23 plus 1 into 35.5 equal to 58.5 unit. Example 3.2. Calculate the formula unit mass of CaCl2. Solution: atomic mass of Ca plus 2 into atomic mass of Cl equal to 40 plus 2 into 35.5 equal to 40 plus 71 equal to 111 unit. Questions 1, 2. Comment this. 3.5.3 Mole concept. Take an example of the reaction of hydrogen and oxygen to form water. 2H2 plus O2 tends to 2H2O. The above reaction indicates that 1. 2 molecules of hydrogen combines with 1 molecule of oxygen to form 2 molecules of water, or 2. 4 units of hydrogen molecules combine with 32 units of oxygen molecules to form 36 units of water molecules. We can infer from the above equation that the quantity of a substance can be characterized by its mass or the number of molecules. But a chemical reaction equation indicates directly the number of atoms or molecules taking part in the reaction. Therefore, it is more convenient to refer to the quantity of a substance in terms of the number of its molecules or atoms, rather than their masses. So a new unit mole was introduced. 1 mole of any species atoms 1 mole of carbon atoms 6.022 into 10 to the power 23 atoms of C, 12 gram of carbon atoms. 1 mole of hydrogen atoms 6.022 into 10 to the power 23 atoms of H, 1 gram of H atoms. 1 mole of any particle atoms, molecules, ions 6.022 into 10 to the power 23 number of that particle, relative mass of those particles in gram. 1 mole of molecules 6.022 into 10 to the power 23 numbers of molecules, molecular mass in grams. Figure relationship between mole, Avogadro numbers and mass. Molecules, ions or particles is that quantity in number having a mass equal to its atomic or molecular mass in grams. The number of particles, atoms, molecules or ions present in 1 mole of any substance is fixed with a value of 6.022 into 10 to the power 23. This is an experimentally obtained value. This number is called the Avogadro constant or Avogadro number, represented by N0. Named in honor of the Italian scientist Amedeo Avogadro, 1 mole of anything 6.022 into 10 to the power 23 in number, as 1 dozen equal to 12 numbers, 1 gross equal to 144 numbers. Besides being related to a number, a mole has one more advantage over a dozen or a gross. This advantage is that mass of 1 mole of a particular substance is also fixed. The mass of 1 mole of a substance is equal to its relative atomic or molecular mass in grams. The atomic mass of an element gives us the mass of one atom of that element in atomic mass units U. To get the mass of 1 mole of atom of that element, that is molar mass, we have to take the same numerical value but change the units from U to G. Molar mass of atoms is also known as gram atomic mass. For example, atomic mass of hydrogen 1U, so gram atomic mass of hydrogen equal to 1 gram. 1 unit hydrogen has only one atom of hydrogen. 1 gram hydrogen has 1 mole atoms, that is 6.022 into 10 to the power 23 atoms of hydrogen. Similarly, 16 unit oxygen has only one atom of oxygen. 16 gram oxygen has 1 mole atoms, that is 6.022 into 10 to the power 23 atoms of oxygen. To find the gram molecular mass or molar mass of a molecule, we keep the numerical value the same as the molecular mass, but simply change units as above from U to G. For example, as we have already calculated molecular mass of water, H2O is 18 unit. From here, we understand that 18 unit water has only one molecule of water. 18 gram water has 1 mole molecules of water. That is 6.022 into 10 to the power 23 molecules of water. Chemists note the number of atoms and molecules while carrying out reactions. And for this, they need to relate the mass in grams to the number. It is done as follows. 1 mole equal to 6.022 into 10 to the power 23 number equal to relative mass in grams. Thus, a mole is the chemist counting unit. The word mole was introduced around 1896 by Wilhelm Oswald, who derived the term from the Latin word moles, meaning a heap or pile. A substance may be considered as a heap of atoms or molecules. The unit mole was accepted in 1967 to provide a simple way of reporting a large number, the massive heap of atoms and molecules in a sample. Example 3.3. 1. Calculate the number of moles of the following. 1. 52 gram of helium, finding mole from mass. 2. 12.044 into 10 to the power 23 number of helium atoms, finding mole from number of particles. Solution. Number of moles equal to N, given mass equal to M, molar mass M, given number of particles N, Avogadro number of particles N0. 1. Atomic mass of helium equal to 4 unit. Molar mass of helium equal to 4 gram. Thus, the number of moles equal to given mass by molar mass implies that N equal to M by M equal to 52 by 4 equal to 13. 2. We know 1 mole equal to 6.022 into 10 to the power 23. The number of moles equal to given number of particles by Avogadro numbers implies that N equal to N by N0 equal to 12.044 into 10 to the power 23 by 6.022 into 10 to the power 23 equal to 2. Example 3.4. Calculate the mass of the following. 1. 0.5 mole of nitrogen gas, mass from mole of molecule. 2. 0.5 mole of N atoms, mass from mole of atoms. 3. 3.011 into 10 to the power 23 number of N atoms, mass from number. 4. 6.022 into 10 to the power 23 number of nitrogen molecules, mass from number. Solution. 1. Mass equal to molar mass into number of moles implies that M equal to M into N equal to 28 into 0.5 into equal to 14 gram. 2. Mass equal to molar mass into number of moles implies that M equal to M into N equal to 14 into 0.5 equal to 7 gram. 3. The number of moles N equal to given number of particles by Avogadro number equal to N by N0 equal to 3.011 into 10 to the power 23. Equal to 3.011 into 10 to the power 23 by 6.022 into 10 to the power 23 implies M equal to M into N equal to 14 into 3.011 into 10 to the power 23 by 6.022 into 10 to the power 23 equal to 14 into 0.5 equal to 7 gram. 4. N equal to N by N0 implies that M equal to M into N by N0 equal to 28 into 6.022 into 10 to the power 23 by 6.022 into 10 to the power 23 equal to 28 into 1 equal to 28 gram. Example 3.5. Calculate the number of particles in each of the following. 1. 46 gram of Na atoms, number from mass. 2. 8 gram oxygen molecules, number of molecules from mass. 3. 0.1 mole of carbon atoms, number from given moles. Solution 1. The number of atoms equal to given mass by molar mass into Avogadro number implies that n equal to m by m into n0. That is n equal to 46 by 23 into 6.022 into 10 to the power 23. That is n equal to 12.044 into 10 to the power 23. 2. The number of molecules equal to given mass by molar mass into Avogadro number. That is n equal to m by m into n0. Atomic mass of oxygen equal to 16 unit. That is molar mass of oxygen molecules equal to 16 into 2 equal to 32 gram. Implies that n equal to 8 by 32 into 6.022 into 10 to the power 23, that is n equal to 1.5055 into 10 to the power 23, approx equal to 1.51 into 10 to the power 23. 3. The number of particles atom equal to number of moles of particles into Avogadro number, n equal to n into n0 equal to 0.1 into 6.022 into 10 to the power 23 equal to 6.022 into 10 to the power 22. Questions 1, 2. Comment this. What you have learned. During a chemical reaction, the sum of the masses of the reactants and products remains unchanged. This is known as the law of conservation of mass. In a pure chemical compound, elements are always present in a definite proportion by mass. This is known as the law of definite proportion. An atom is the smallest particle of the element that cannot usually exist independently and retain all its chemical properties. A molecule is the smallest particle of an element or a compound capable of independent existence under ordinary conditions. It shows all the properties of the substance. A chemical formula of a compound shows its constituent elements and the number of atoms of each combining element. Clusters of atoms that act as an ion are called polyatomic ions. They carry a fixed charge on them. The chemical formula of a molecular compound is determined by the valency of each element. In ionic compounds, the charge on each ion is used to determine the chemical formula of the compound. Scientists use the relative atomic mass scale to compare the masses of different atoms of elements. Atoms of carbon-12 isotopes are assigned a relative atomic mass of 12 and the relative masses of all other atoms are obtained by comparisons with the mass of a carbon-12 atom. The Avogadro constant 6.022 into 10 to the power 23 is defined as the number of atoms is exactly 12 gram of carbon-12. The mole is the amount of substance that contains the same number of particles, atoms or ions or molecules or formula units, etc. And there are atoms in exactly 12 gram of carbon-12. Mass of 1 mole of a substance is called its molar mass. Exercises. Do this and comment this. Group activity. Play a game for writing formula. Example 1. Make play card with symbols and balances of the elements separately. Each student should hold 2 play cards, one with the symbol in the right hand and the other with the balancing in the left hand. Keeping the symbols in place, so students should crisscross their balances to form the formula of a compound. Example 2. A low-cost model for writing formula. Take empty blister packs of medicines, cut them in groups according to the balance of element as shown in the figure. Now you can make formula by fixing one type of ion into another. For example, Na plus SO4 2 minus PO4 3 minus. Formula for sodium sulfate. Two sodium ions can be fixed on one sulfate ion. Hence the formula will be Na2SO4. Do it yourself. Now write the formula of sodium phosphate. Do this and comment this.